Kraettli Epperson. I'm the CEO of Vigilant Aerospace, and I'm going to be presenting about onboard detect-and-avoid systems for unmanned aircraft focused on advanced air mobility, urban air mobility. I wanted to thank SAE Aerotech for the opportunity to present this today. I'm going to try and leave a little bit of time for Q&A at the end, but I will be going pretty quickly because we have a lot of material that I'm going to present. So topics I'm going to cover, I'm going to focus on what is detect and avoid, so a little bit of introduction, background on our company and our product that we use in the testing that I'm going to be discussing, talking about typical detect and avoid processes and cycle and why that matters and how it works, background on the technology and the prior field testing and so the new field testing that we've been doing, which will really be the heart of the presentation. Then I'll talk about some emerging trends and then our future roadmap for development of this technology. So a little bit of introduction. What is detect and avoid? So detect and avoid is a foundational part of autonomy for uncrewed aircraft systems, expected to be foundational technology for AAM and UAM in the future in order to allow these aircraft to fly safely with a high degree of assurance. So it allows uncrewed aircraft to detect other aircraft beyond visual line of sight. So that's really the fundamental job. It's a requirement for safety. It is designed to help aircraft remain well clear of manned aircraft. It's typically designed to detect both cooperative and non-cooperative. So when we say cooperative aircraft, those are aircraft with transponders that are transmitting into an air traffic control system. Non-cooperative are aircraft without a transponder that would otherwise be detected using some sort of active sensor. We'll talk about that a little bit. So onboard DAA specifically is very important for the future of the industry because it makes long range beyond visual line of sight practical without needing to, for example, set up significant amounts of ground infrastructure, existing radars in just the places that you want to travel, or other infrastructure to allow you to remain safely aware and away from other aircraft. So onboard is what we feel is a very important frontier. It also needs to be scalable. Onboard detect and avoid is highly scalable because it goes on the aircraft and does not require a lot of preparation ahead of time. And the systems must be trustworthy and well tested. That's an important part of what we'll talk about today. These are critical safety systems, and it's understood in the industry that there is a great degree of testing and trust that has to go into these systems. So a little bit about our company. We're Vigilant Aerospace Systems. Our product is called Flight Horizon. We're focused on developing detect and avoid in airspace management systems. So airspace management both for ground-based and detect and avoid for both ground-based and onboard. Flight Horizon is based on 2 NASA patents that we've licensed and has active use now at NASA. We've used it in FAA projects in the UAS test sites, which are spread across the United States, and their development programs. We're focused on highly integrated multi-sensor systems. So as I talk a little bit more about what we've been testing, you'll see some of those sensors. It uses both ground-based and onboard versions. And it uses both local sensors and increasingly online data as that's available. And we're very interested and aware of UTM development and collaborative systems that are emerging. And we really focus on industry technical standards and current market needs as we develop our DAA system. So this is a diagram of our system. The system is designed to allow unmanned aircraft to detect and avoid other aircraft beyond visual line of sight. It is the software in the middle of that orange triangle, the orange rectangle, is the core of the system, and that's really Flight Horizon. And it takes in information from multiple other systems and sensors. We don't develop the hardware, we are focused on the software, and we buy the hardware off the shelf, and we partner with companies who develop the various sensors and transponders. So on the left-hand side of the diagram there, you'll see an autopilot. That is providing telemetry, and we'll pick that information up either directly from the autopilot or from a ground control station if there is a ground component. And I'll show you some pictures and diagrams of the system on board and on the ground. In the middle there is a portable radar. We integrate with those small portable radars like this one, which we use for field testing, and with larger radars. And then on the right-hand side there, you'll see a receiver for transponder signals from larger aircraft, mini GA, commercial aircraft. Most of them are required to have transponders, and so that's a baseline technology we can use to provide awareness All that comes into our system and is updated live to provide an airspace picture, and then to provide calculations of trajectory predictions, and then ultimately resolution advisories or maneuvers for avoidance are provided to the pilot or to the autopilot. So as we develop this system, we're very much focused on autonomy, so that all these things can come together in the software and provide what's needed, either to the pilot or the autopilot. Typical DAA cycle will be to collect the information from the sensors, parse the data, index the targets, build the trajectories, and predict the potential collisions, iterate strategies to issue an avoidance command, and then to monitor and maintain that self-separation. And this is going on multiple times a second in our software. And that's why I put that up there, is just to give you an idea of what it's doing, and it's doing that continuously. Typical components, we often get questions about this. So basic components would be the autopilot itself for the control and telemetry information, and then non-cooperative aircraft sensors. These might be a radar, like the ones that I've shown here, might be an EO/IR, an electro-optical or infrared camera system. Those are also used for shorter range detection in some cases, and then acoustic systems and RF systems. RF is mostly used for counter UAS detection when you're detecting road drones. But all of those are used as non-cooperative sensors. And cooperative sensors typically are going to be your transponders on board, so that you can detect cooperative aircraft that are participating in air traffic control. And then increasingly, of course, we're very interested in integrating UTM as more information is being broadcast into a network system. And remote ID I don't include here yet, but we have a partner in projects this year that we're doing for several entities to integrate remote ID, which is going to be kind of important for UAS over the next year. Here's some pictures of us setting up to do some field testing. On the left-hand side, this is a typical small-scale ground-based test. You have the ground control station for the uncrewed aircraft on the left-hand side, you have telemetry radio, and then you have our software, Flight Horizon Commander, at the center on the right-hand side there. You have the ADS-B in, so that's your transponder receiver, and you have the portable radar. And those three data sources are informing the software so it can perform its job continuously and provide that live picture. On the right-hand side of the screen there, you'll see a picture of the same setup, but fully on board. This is work that I'll describe in a few moments, but this was a live beyond visual line of sight flight that we did, and this has the ADS-B in receiver, has connection to the autopilot on board, has onboard radar, and has our software running on a single board computer that is integrated with all of those inputs and continuously performing its function on board. So this is a little bit of information about the user interface that we typically use. It gives you an idea of what the software is really doing, and I'll show you a quick video in a moment. So airspace visualization is being provided. So you can see here in the middle, there is a small white arrow. That is your own ship. It is surrounded by two hockey pucks or cylinder shapes. The yellow one is your well-clear distance. This is a safety distance from other traffic. You don't want other air traffic to come into that. If you do have air traffic that is threatening to come into that, then the system is going to issue a command to avoid that encounter. The red cylinder in the middle there is your NMAC, is your near mid-air collision cylinder. You definitely don't want aircraft in there. On the left-hand side, you have a detected aircraft that is coming in. There's a blue line that's the predicted trajectory of that aircraft, and then the system is issuing a warning and issuing a resolution advisory. That's the red box at the top there, and that'll do a countdown through the entire encounter. We'll also be tracking for other aircraft and be able to provide that command. It's also producing waypoints that can be sent to the autopilot. So this is just a representation of a fully autonomous process that can send these waypoints for avoidance to the autopilot. This is a video I'll play for you very shortly. So you'll see that the white aircraft is engaging in an encounter with an intruder aircraft that's been detected. The system is warning on that, providing a resolution to turn left and speed up immediately in order to avoid that blue intruder aircraft coming into that yellow cylinder. So that maneuver has been executed and the encounter is avoided. There's no loss of well clear, and the system is able to continue monitoring, and the UAS returns to its its original flight path. So that's an example of a full encounter in just a few seconds there. Gives you an idea of how the system works. These are some other interfaces. These are alternatives that you can use with our system. The one on the right-hand side is for multi-ownership, so you can have any number of uncrewed aircraft that you're tracking in this system and be able to do collision avoidance for all of them. And then on the left-hand side is more of a traditional TCAS, ACAS system. This is something that we've been asked for. Many pilots are familiar and comfortable with this interface, and so we've implemented this and we'll continue adding features to that. So very briefly, I'll mention the industry technical standards. These are standards that we track. These are developing all the time, and there are new ones emerging. And obviously, one of the reasons that we're very interested in coming to this event is because we're very interested in the standards that SAE is developing. ASTM has developed several relevant standards that have been published now and is working on several additional standards. The F3442 standard is the Detect-and-Avold standard, version 1.0, that was published in 2020. I served on that working group and now serving on the version 2.0 of that working group. There are also other standards for assurance of software compatibility and interaction with ground-based radars through a UTM system, and then also standards that are emerging around how you test your system to determine that it meets these standards. So I'm also on a working group for that. And that's very important. It's been obviously very useful to us to understand what types of reports and artifacts we'll be generating over time to demonstrate that we comply with these standards. Our TCA has standards. Typically, ASTM is focused on smaller UAS. Our TCA tends to be focused on traditional aircraft and larger UAS. The DO365B standard is the primary standard that we track. It's the Detect-and-Avoid system standard. The algorithms that we use, for example, are compliant with that standard. They're actually a reference. The algorithms that we use are the reference installation for that standard. And so that gives us great compatibility. It provides assurance to us and to our users that we have implemented a system that they can use with the right configuration and the right equipment to meet these kinds of standards. Several other standards that we're exploring, depending on what equipment, including ground-based equipment, is available, including sensors that can be implemented and used with systems like ours. So when we test Detect-and-Avoid systems, how do we do that? What are we testing for? There are really two types of tests that we typically engage in. We look at sensor testing, and then we look at system testing overall. So sensor testing involves a variety of radars, EOIR systems, acoustics detection. This gets tested all across the industry. We typically focus on 2 or 3 things, which I'll show you, I've shown in these diagrams. Typically, you're looking for range of first detection, so when you first are able to identify an intruder aircraft that might present a threat to your aircraft, and your ability to create a track out of those detects. Is the detection consistent enough that you can create a track and generate a resolution advisory if needed? So those are things that we watch very closely. We log all of our data. This is actually a picture from some of the testing that we did under an FAA contract with lots of different systems being logged. And then we look at track filtering and classification. This is a very important function in order to determine that you're not tracking a bird, determine that you're tracking the things you're supposed to be tracking, and figure out what to do about them quickly. And then system testing. So as a system integrator, we really focus on how the overall system works. That's absolutely critical for being able to meet the industry standards. That 3442 standard has both a risk ratio as a target for that, and it also has a timing budget that you've got to be able to reach so that you can provide safety adequately with your system. So we look at the traffic alerting process and the warning process. We look at whether the algorithms are doing what they're supposed to do. We look at track correlation. Track correlation is the process of being able to detect an aircraft with multiple systems or sensors and tell that it's the same aircraft and only track and display and use for warnings one of those 2 tracks. So very important, otherwise you'll be continuously having false alerts on your own aircraft. For example, when you have telemetry coming in and a radar detection, you you have to be able to ignore the radar detection so long as you have used your algorithm to determine that's your own ship. So we look at the resolution advisories to be sure that they're working correctly, and then the ability to carry out the avoidance maneuvers. Our software, for example, allows you to characterize your aircraft, and so you have the performance of your aircraft. If you have a minimum speed, a stall speed, if you have ascent rate, descent rate, maximum speed, minimum speed, all of those things go in to the software so that it can design a resolution advisory that your aircraft can carry out. It's not very useful if you have a resolution advisory that you can't do. All right, so this is some information on some recent tests that we've done. This was a beyond visual line of sight flight test under a Part 107 waiver, so this is fully beyond visual line of sight under Part 107. This was carried out as part of an FAA research contract that was done along the Trans-Alaska Pipeline with a quasi at University of Alaska Fairbanks. They're a great partner for us and many other developers of these types of systems, and they're one of the federally recognized test sites. So this was an FAA-sponsored project where we were flying our Flight Horizon Pilot, which is our onboard system, over multiple miles with no visual observers. We had a variety of sensors in place, including radars. We were testing multiple predicate radars for this project for the FAA and for integration to our system. So this was the first flight beyond visual line of sight of a small UAS under Part 107 with an onboard radar-enabled detect-and-avoid system. So we're really proud of that. We did that middle of last year, and that was a fantastic project for us. And we provided reporting to the FAA and to the test site program on that project. This is a little bit more about that. We were testing encounters against helicopters and against GA aircraft, so this is the 172 type of aircraft. With the onboard system and with ground-based systems, we had 3 different radars we were testing, and we were tracking and logging all of this, including flight data recorders, UAS telemetry, radar logs, ADS-BN logs, and all the conditions. It was very cold in Alaska, which presented some additional special challenges for us. This is a little bit of the type of information that we collected. So we did analysis of the radar tracks versus actual tracking of the aircraft, analysis of the range of first detection of the GA aircraft and the UAS in some cases. So in some cases, we were actually using a small UAS as a test aircraft in addition to the GA aircraft. We spent a lot of time on filtering and filtering effectiveness. This is something that's very important for eliminating clutter and removing false tracks. And then overall analysis of the system effectiveness with that filtering in place. We did a lot of analysis afterwards, comparing these various data sets to each other to be able to provide this reporting to the FAA and ultimately hopefully be able to impact the types of rules and regulations that will become available for industry to use as these types of systems are in the marketplace. And ours is in the marketplace now. This is another set of testing we did recently in 2021. This was with the Mid-Atlantic Aviation Partnership at Virginia Tech, another one of the federal UAS test sites. There were multiple companies testing detect-and-avoid systems at the MAP farm. We had 80 small general aviation encounters over a couple of days. We were using a radar on a mast. We were using ADS-BN. We were using direct connections. And in fact, in that picture, we're sitting right next to the pilot, so that we can provide direct feedback on our resolution advisories. We have offsets of various kinds, so this testing is done in a way that is very safe, it's very controlled, so we know where the aircraft and the unmanned aircraft are at all times. We tracked and logged all of this as we always do, and we're able to provide that information in real time to the evaluators. We were very pleased with these tests. So a little bit more about some of our other work. We've been involved with the Alaska UAS Test Site and their Beyond program, which is the new program. It is the successor to the IPP program, the Integration Pilot Project program, that ran from 2018 to 2020. We also have a system that we're installing with Northern Plains UAS Test Site. This is a third of these federally recognized test sites, and that's us handing that system over and getting ready to start using it with them. And we've been involved in many NASA programs. NASA uses our system, particularly with their supersonic program. They do a lot of their flight tracking in our software because they can log it all and then they can correlate our logs with all the other supersonic data they've collected, particularly about sonic booms and other things. And it also provides safety for them so they can make sure nobody's violating their TFR experience for us. Some information about the advantages of automatic detect and avoid for safety and autonomy, and that's really obviously one of the important themes for this event is autonomy and AAM. So a system like ours provides integration of the autopilot, telemetry, and lots of logging, so it really provides better safety than a system that is not fully integrated. It's aware of its own location and tracks distances to other aircraft and predicts trajectory, so it can provide a high degree of autonomy. It automatically calculates these resolution advisories and maintains separation, so it's not pinging on one screen and then somebody grabs a joystick or otherwise takes an action based on what they perceive to be going on one of these screens, which is how a lot of detect and avoid has been accomplished over the years. The system is fully integrated and enclosed so that it is receiving all the information and can send the exact resolution advisory out. And that we feel is very important. It's really a baseline for autonomy. To be able to move autonomy forward is to be able to have this kind of automatic safety. And it continuously recalculates multiple times a second to cut down on that delay and latency that you might have. So it takes a deterministic approach to maneuvers. It's using maneuvers that are a part of the existing standards and uses those tables. So you know what it's going to do and you know that it's going to take the maneuver that is essentially approved. It follows industry standards and uses those algorithms. All of these standards and all the DAA systems, ultimately what they're trying to do is reduce the closest point of approach of that intruder aircraft after it's been detected and determined that it might be some sort of threat, that it might come into your air volume. And so that's ultimately what it's doing, and that's why these systems can be proven to be effective, is because you can measure that CPA, and that's a typical measure that's used in this type of testing. We really believe that these types of systems need to become a baseline function in autopilot systems and really to enable autonomy and enable the next stage of AAM in the US, that these types of systems are critical for that to happen. Some important emerging trends in the industry. So there are regulatory changes that are coming down. These are very exciting. I recently served on the FAA's Beyond Vision Line of Sight Aviation Rulemaking Committee. That report has just been published a couple weeks ago. It has recommendations for new rules for Beyond Vision Line of Sight of uncrewed aircraft, specifically focused on low population density areas. But it has a lot of trade space, a lot of different ways that you can use those recommendations when they become rules. And we think that's going to be fantastic for the industry, and we certainly expect that it will begin to influence the issuance of waivers and other sorts of things that the FAA is able and willing to do now that it's been published. There's also obviously a lot of emerging excitement in the market between UAM and AAM flights. We believe that the interest is very high right now in the market because of the ARC and because of other developments, just the maturity of the technology. And so that's really creating opportunities for this type of technology. There is a lot of critical development, testing, and prototyping that's going on across the industry. A lot of that's been highlighted at this conference. And then there's a lot of ML and AI opportunities, particularly around vision systems, to be able to add additional layers of safety. All of this is multi-layered safety with multiple systems and detections. And so machine learning and AI will certainly begin to contribute to that. All right, so finally, a little bit about what we see as the roadmap forward for the industry. So regulatory experience helps to, controls the speed at which these things are developed. And so we know that these initial Beyond Visual Line of Sight recommendations moving to rules will be a very important waypoint for AAM. We have seen this before. The FAA will implement one set of rules with the expectation that they will inform the next set of rulemaking. And so we are very excited that we're now in that process. The recommendations going to the FAA, rulemaking will then take place, and then the FAA will be able to begin to watch lots of Beyond Visual Line of Sight flights and what level of safety can be achieved, what technology can help do that, to then begin to inform the next set of rules to enable AAM, and then ultimately UAM for higher density, population density areas and much more advanced, sophisticated flights, moving into eventually air taxis and things like that. We're also excited and see a lot of promise with the collaborative approaches to air traffic management, like ETM, and that we believe is going to emerge as a very important part of UAM particularly. There's also a lot of changing technology. This is something we have to track because we're trying to use and implement the this technology all the time. So better, smaller, lower powered sensors, including radars. Radar on a chip is something that is being talked about in the industry. Better, faster, more reliable machine learning-based classification, more computing at the edge to allow you to take large amounts of very sensitive, discrete data and then push forward only what's required and necessary. More powerful for computing and then ubiquitous 5G connectivity is very important. And then finally, more of these collaborative technologies as they emerge and become a part of what can be used to provide additional data. So that is my presentation. Thank you all very much for listening.